Well, we can go back up here and look at our equation, and we can rewrite it using these definitions instead of using these definitions, and we're going to get something like the square root of f prime t star delta t, this quantity squared, plus g prime t star delta t, this quantity squared. Okay, that's our line segment. And then if we were to sum over all the possible line segments along the curve of interest, this is going to get our estimate. Notice that this delta t is squared in here, this delta t. We can factor this out, a delta t squared, but then we can bring it out of the square root sign. So this becomes then sum of f prime t of our special point squared plus g prime t of a special point squared. If you prefer, you can throw in some extra things to make sure we're not squaring the t. We're squaring the whole thing times delta t. And that is a discrete way of representing this. But if we think about our ideas of limits, we can say, well, what happens in the limit as we make these time slices thinner and thinner and thinner? Well, the sigma becomes a integral sign square root of f prime of t quantity squared plus g prime of t quantity squared dt, and we've got our definition for the length of a line segment. As long as we can integrate this, we're going to be able to define the length of a line segment using calculus. And one thing I might note here, if you're a purist, you'll notice that I use t star and t star here. Actually, probably I should have used a double asterisk. Technically, of course, the point where the mean value theorem is going to pick where the slopes are equal to the average slope is not exactly the same, but that problem goes away at the limit, and then we just plug in t. So yeah, a little technical mistake there, but I think this gives you an idea, and we can now proceed with some examples.